All right. You know, storage is cheap. The reason why I say storage is cheap is that it's relatively easy to acquire. The hard part is actually managing the data for this full life cycle stuff. And that's actually the hardest part. Operationally, even though storage is sort of going cheaper and cheaper at a sort of radically increasing rate, the operational costs, the staff costs, the tape costs, the backup costs, the replication costs are still sort of remaining roughly the same. And I think I still reserve my biggest amount of respect to kind of the backup administrators who are sort of staying afloat in the age of these, you know, $120 1 terabyte SATA disks that you can go buy from Costco these days. A personal mission of mine is every once in a while I head out to Costco and I find out how much a terabyte's going to cost. It was $220 in August '08, and now the last time I went, it's about $124 at the Costco nearest to me. The reason why I put this slide up, particularly for the IT professionals in the room, is that many end users' expectations about the cost of storage are set by what they see at Best Buy, Newegg, or Costco. So they're coming to you with an expectation that a terabyte of data is not a big deal. It's $124 from Costco. They don't understand that, you know, to do that at an enterprise level, to replicate it 4 times, to put it on tape, you know, you're starting getting to costs where, you know, a terabyte of storage, it might be $5,000, it might be $40,000. It's very, very significant. And one of the things that we really sort of strongly recommend is IT organizations really need to sort of help set expectations, because the personal electronics market is wildly skewing people's expectations when it comes to storage, particularly when it comes to cost and budget. And you will see this most often when people who are writing grants for next-gen sequencers who don't budget for storage and backup. And that's one of our biggest sort of, you know, SWAT team type problems where we solve is these people get an instrument in, they're now generating 10 terabytes a week, and they haven't really budgeted for, you know, a 50 or 60 or 100 terabyte or even larger storage system to put all that stuff on. I still see individual labs putting in 100 terabytes or more of storage, even for a single next-gen sequencer or, you know, a couple of ultrasound machines. A couple years ago, I said petabyte scale storage would appear within the decade. That's old news. I mean, Broad has multiple petabytes. There's many, many people in this room who are either at petabyte now or will be petabytes, you know, within a year or two. Another homework exercise I'd like to give to you is, for you, those of you who are interested in this field, is pick any 3 storage vendors that you like and find out how much it would cost for you to get 100 terabytes. I figured out that if I built it myself with tier 2 stuff, I can get 100 terabyte single namespace for about $160,000. Putting together quotes from other vendors, I can get that price anywhere. I can get it close to $2 million if I want. It's an amazing SKU, and one of the things I personally try to do is I repeat this experiment every 6 months just to see sort of how the numbers change. I've talked a little bit about this before. Really, this is the message. Unlimited data storage in a scientific environment is over. I can buy disk fast enough. I just can't back it up, replicate it, keep it safe, keep it secure, and keep it available at reasonable cost. It is now pretty much a given. And actually, in terms of questions and back and forth, I'd love to find the outliers. The great thing for me is that everybody I talk to has basically come around to the same conclusion. There are absolutely some cases where it makes sense to go back to the -40 freezer, repeat the experiment, than it does to actually keep this stuff online forever. And one of the nice things about what we're seeing in 2009 is that this data triage stuff, it's a given. People are starting to think about it. Scientists are having discussions with IT staff, and they're sort of mapping out realistic life cycle planning for scientific data. The data loss, the big thing for us in 2008, irreplaceable loss of more than 10 terabytes of scientific data. I put fired in quotation marks because it was a government lab, and you don't really get fired as much as your contract doesn't quite get renewed and you take the hint and you sort of walk out the door. The very simplified root cause was a double disk failure in a RAID 5 volume that held the metadata for the SAN. And the reason why I'm setting that up with a little bit of, and there were significant operational errors in that there are indications that people entered the machine room and silenced audible alarms without fixing the problem that was causing the audible alarm. So technological problem and operator error definitely caused the problem. What this means for me, as I mentioned, is that if you had seen me talk 5 or 6 years ago, I was a huge fan of RAID 5. In life science workflows, we read far more than we write, so RAID 5 was the perfect RAID level for me. 2009, actually starting in 2008, BioTeam no longer uses RAID 5. We're at the point now where we have more disk drives than ever, and we're at the point now where the statistical probability of a double disk failure in a RAID 5 volume, it's not, it might happen, it's going to happen, and it's going to happen in your organization. RAID 5 is no longer acceptable at the level of drives and the level of storage that we're doing. Everything we do now is RAID 6 or other double parity system. And then finally, I won't walk you through all the other bullet points, but basically, Because of that lesson, we are incredibly aggressive now about proactive storage monitoring. We replace disk drives when they throw warnings. We don't mess around. I don't even consider lower-end storage products that don't offer background disk scrubbing and other sort of integrity stuff behind the scenes. And finally, there's a lot of storage arrays out there where you kind of don't turn on the email reporting or the alerting, and we're absolutely religious about that stuff now. But probably the biggest lesson and the biggest thing that I want to push out is that it's RAID 6 or double parity. I mean, RAID 5, you're setting yourself up for a big old disaster. As the number of drives increase, the statistical chance of losing 2 at the same time rises to basically an almost certainty. Talked a little bit about this. One of the reasons why, I think the exponential growth that we've been seeing, it's starting to get a little bit easier to get your head around. There's better data reduction happening within the instrument, so we're no longer generating the 10 terabytes that has to be distilled down to the 1 terabyte that you actually want to keep. Software RAID is actually starting to become a little bit more prevalent. And one of the more interesting trends that we've seen here is that people are actually running clever bits of software that I might actually need within storage products themselves. And, I'll use Isilon as an example, BlueArc as an example, but Ocarina's reader software is now running within the Isilon node, so you can get the Ocarina stuff without having to deploy anything else. And same thing, there was a press release the other day. Ocarina's full-on optimizer stack is now running natively within BlueArc chassis. And that's one of the trends that we're going to start to see. I mean, even looking at the Sun 7000 series Amber Road stuff, more and more intelligence and more actual applications or services are actually moving into the storage products themselves. All right. Backup. The only thing I really want to say about backup is that, we're at a point now where we have new expectations and new procedures. We are in an age where nightly fulls may never happen again. When you're in the multi-hundred terabyte, the multi-petabyte stuff, nightly fulls just starts to become completely unreasonable from a backup perspective. A good example for me recently is 50 terabytes of Isilon storage. Now, Isilon storage is this fast, parallel, scalable stuff. It's very, very high-end storage. We're working with a customer now that's treating it as scratch space. It is absolutely not backed up at all. And it's because they've made the realization that, they need the speed, they need the scalability, but the users have been told, look, it's scratch space. There are other places, there are other blessed enterprise locations for you to put your source code, your applications, your data. This high-end 50 terabyte parallel storage, scratch space only. You put something on there and the storage goes away, you're out of luck. One of the more interesting things when it comes to cloud storage is there's an Amazon blogger, James Hamilton, has sort of done some back-of-the-envelope calculations, and he's sort of figuring that the companies like Amazon, Google, and Microsoft can do geographically replicated cold storage at a cost of 80 cents a gigabyte a year and falling. And that number is important because I think that number is far cheaper than typically what it would cost to do that in your own data center. And there are interesting use cases for cloud resident storage if these numbers actually come out. And this is important. This is data distributed across multiple geographically separate data centers for 80 cents a gigabyte per year. It's very, very difficult to get that level of economy of scale in your own data center, your own operating environment. The two message points that I want to talk about really on this slide is that when it comes to storage and it comes to science and it comes to IT, IT cannot be the sole decision maker. And there's two areas where you really can't have IT be 100% in charge. When it comes to matters of data triage, obviously, you don't want the IT team making the decisions about what scientific data is kept and what scientific data is discarded. That has to come from the science up, and it has to come with full buy-in and full support from the scientists there. So one of the things we really, really strongly recommend is when it comes to data triage, you got to start with the scientists, you got to get their buy-in, and IT should be there, but they shouldn't be taking the lead. And same thing goes for aggressive storage optimization efforts. My particular story here is that a virtualized environment where they were making really aggressive use of thin provisioning. They were over-provisioning storage to users, which was more than they actually had. In this case, a scientist was given a server. The server was given an iSCSI volume with 500 gigs. This scientist decided to put 500 gigs of data in the volume that she was allocated. Because of the thin provisioning limit, there actually wasn't 500 gigs available, and she crashed not only her whole system, she crashed the entire virtualized infrastructure. And see, I have a problem with that. I understand the benefits of thin provisioning. I understand deduplication, but I also have a problem with offering a scientist n number of x and then crashing the entire system when n number is not actually available. So one of the things that I've sort of a lesson learned from that is that if you're going to be very, very aggressive about content optimization on your storage, you need to have buy-in from the scientists. And in particular, you shouldn't be offering 500 gig storage volumes that don't actually expand out to 500 gigs without crashing catastrophically.